Thank you. Hello. Good afternoon. Of course. So, in the same fashion that I just explained, we already know that, of course, because of the Lorentz transformation, so the Lorentz transformation actually has to follow some very specific rules, you see. So the space-time interval, which is what we keep constant in general relativity, this thing has to stay constant, is equal to this. And of course, c here means the speed of light, t is time, x, y, and z are the three space coordinates. And of course, this is just a small variation from regular Euclidean space. So then, what we can do is we can use what we call the Minkowski metric, which looks like this, to encode this information in a better format. So how does this have anything to do with that, of course? Well, it's very simple. All this is just you take dt, dx, dy, dz, and then you multiply the metric in the middle, and then you get the row vector dt, dx, dy, dz. And of course, you can do the maths by yourself, but all this does is simplify to this form. Okay, so what we're actually going to do is use Gaussian coefficients, which is going to remove the speed of light or set it to 1 instead so that we can work in peace. And so now all that's going to happen here is that this is just going to have to be equal to the regular metric weight. Oh yeah, so all that's going to happen here is that this has to be equal to, of course, just this space-time interval right over here, which means something very special. Right? So what I'm going to do is I'm actually going to write this as this, which is an abbreviation for all of these, times the metric, which looks like this, times this, which is just a row vector instead. So that means it's the transpose. And this has to stay constant, right? So that means that once we apply the Lorentz transformation, just like so, let me just rewrite this. Why do I hear people giggling? So if we reapply the Lorentz transformation, what we're going to get is something like this. Oh, this is in the wrong order. Of course, once you take the transpose of these, it's going to be in reversed order, which gives us something like this. And this has to be equal to the normal format, because of course, everything has to be conserved, which leaves us with the special equation that this, the Lorentz transform times the Minkowski metric times the Lorentz transpose has to be equal to this. And of course, this is a very special class of matrices. And of course, all we do is in two-dimensional coordinates at least, we set this to just be equal to some matrix with components A, B, D, F, for example, which means the transpose is going to be A, B, A, D, B, F. And of course, then we just solve for it using the regular Minkowski metric. Now in the 4 dimensions that real relativity uses gets a lot more complicated, so we usually just use computers, but this is a nice exemplary example. What did I just say? So then it turns out that what we get is going to be, end up being something in this format. It's going to be some constant, 0, 0, if I remember correctly. And then, oh wait, no, this is the identity. It's going to end up being something like this. And then over here, we're going to get a proportionality constant, beta squared, that's what I do. But whatever it is doesn't matter. The fact is, beta is going to be very important because it's equal to the square root of 1 minus v over c squared. And so what we call the gamma factor is just 1 over this. So then this gamma factor is responsible for dilating every single quantity. So that includes mass. Mass itself might seem like a scalar, but it itself has to be dilated too by this, because this is actually sort of dilating not mass in specific, but what we call the stress energy tensor, the mass energy tensor. This, which encodes all of the mass and energy in a 4x4 format, which essentially has a lot to do with the Maxwell's equations for electromagnetism. So the point is, we multiply this proportionality constant by this, which is essentially what mass is. And so that means that, in essence, we're multiplying mass by the regular mass times the speed of light. So the rest mass times, not the speed of light, oh my goodness, the gamma factor, which is this. And of course, as you said, why does mass approach infinity as velocity approaches c? Sorry, I think I'm dying of heat stroke. So why is this true? Well, of course, if you look closely, you'll observe that beta is going to approach 0 as v approaches c, because this is 1 minus v over c squared. So of course, if you plug in c, this is just going to give you 0, because the c over c squared is going to be 1, you see it. So since gamma is 1 over beta, then as v approaches c, gamma is going to approach infinity, because of course the denominator is getting smaller while the numerator stays the same, which means it's going to go up and up and up and approach infinity. So that's essentially a short answer for why mass approaches infinity. Thank you.